Alright, this is a continuation in a series of videos whose express purpose is to show you how to solve various kinematic problems effectively and quickly using the SUVAT method. Quickly is the big problem with kinematic problems oftentimes. I'm assuming that you've seen the part 1 video, which is an introductory video, and so if you haven't seen that, I encourage you to do so. And in it, what I do is go over quite a few topics. I go over the merits of the SUVAT method and the rationale behind it, and also review general kinematic concepts and terminology that's often, some physics terminology that often is confusing to students I tutor and was confusing to me, so I thought I'd address those in the video. And if you want to pause your video to read this in more detail, if I'm scrolling too fast, then do so. Okay. Alright. Let's just remind ourselves that when you discern whether you've got a kinematic problem or not, where you can use the SUVAT method, you're looking for constant acceleration or constant deceleration, and then you need at least 3 out of the 5 SUVAT. 3 out of 5 of those: velocity, displacement, time, initial or final velocity. You're not dealing with forces, you're not dealing with mass or energy, so there's no newtons or kilograms or joules. Those forces are involved with dynamic problems and static problems, and so anyway, that's mentioned in the introductory video. The 4 steps for the SUVAT method: 1, write the SUVAT vertically. 2, enter 3 out of the 5 variables next to their letter. You'll have to find 3 to do the problem. Step 3, circle the variable you need, and 4, draw an arrow through the variable that's left and use the equation that's affiliated with that variable to solve for the circled variable in 3. So you'll have something that looks like that, something that's similar to that after each problem, or before you solve for the equation. But it points right to the equation you need. Hopefully by this time, if you've been following these in order, these videos, you've memorized these equations. Eventually that's the thing you've got to get to the point of being able to do. And so the SUVAT method is essentially just a simple, almost algorithmic way of quickly pointing you to the right equation when you really need to find it fast. Okay, so our first problem today is a 2-part problem. A particle moves with a uniform acceleration at 0.5 meters per second squared in a horizontal line ABC. The velocity of the particle at C, right here, is 80 meters per second, and the times taken from A to B, 40 seconds, and B to C, 30 seconds respectively. So we want to calculate the velocity at A. So we're interested in the problem at this point. A is where the particle begins, and so we'll call this our initial velocity, U. This is our final velocity, and we have some elements of information with time, and we've got acceleration there. And of course, first thing you do is make sure you've got constant or uniform acceleration. So yes, this is a SUVAT problem. So we fill in the information that we need, or that we have been given after we line up step 1, our vertical letters. We have final velocity 80 meters per second. We have 0.5 meters per second squared acceleration, and we also have, even though it's broken down, kind of throws you off, we have 70 seconds worth of time that surpassed from A through C. So we can go ahead and put those two together, and that's how much time's transpired. We're going to step 3. We're looking for what? We're looking for the velocity at A, our initial velocity, and then step 4, we're going to draw a line through the remaining variable and employ the kinematic equation that goes with it. For us, this would be final velocity is equal to initial velocity plus acceleration times time. So we'll go down here and we'll take a look at this math for this first first question, and we fill in V, we fill in A, we fill in T, and solve for U. And so we've got seconds times seconds squared, and so one of the seconds will cancel out on the bottom, and so we got meters per second. 0.5 times 70, 35, and then we got 80 meters per second. We're going to do our little algebra. I'm assuming you know how to move things around. We'll solve for U. So we're going to subtract minus 35 from both sides, meters per second. So we end up with that on the left, and we find our initial velocity is 45 meters per second. So our second part of the problem is finding the displacement between B and C. Okay, so we got to be careful this time. What do we have? We actually have found some information in the first part of the problem. You know, we found the initial velocity was 45 meters per second. But whoa, wait a minute. Don't jump the gun. That's what it is here, 45 meters per second. But we're interested in the time interval between here and here, so we can't use that. Okay, so that's what's good about this problem. People might fall into thinking that they can employ that initial velocity we found. But what we still are okay. We got our acceleration because it's constant of 0.5 meters per second squared. We've got our final velocity, which is 80 meters per second here, and we do have a time interval. We've got 30 seconds. Okay, so we've got 3 out of the 5. And we are solving at step 3. We're going to circle what we need. We need displacement. So we're going to circle that, and step 4 is draw a line through the variable that's left, and so we're going to employ an equation that doesn't get used that much with the SUVAT method or in kinematic problems. Is displacement is equal to final velocity times time minus 1/2 AT squared. Okay, so we're going to use that, and notice this is the equation we're using, and it's very similar to the third kinematic equation. The only difference is one's plus and one's minus, and second one has final velocity, and the third one has initial velocity, but they're almost identical. So we're using the second one, and we're going to fill in the information that we have. We've got final velocity, we've got time, and we're solving this for the displacement of BC. We got acceleration, and we got time again squared. So we're going to multiply that, and seconds cancel out, 80 times 30. So we've got meters, and we've got seconds squared and seconds squared, and so those are going to cancel out, and again we're left with meters. And so we end up with 225 from that, minus the 2400 minus 225, and so we find that our displacement from B to C is 2,175. Now what I'm going to do is I'm going to go down here and show you if we did A to C. I'm not going to go through it all, but if we wanted to do A to C, you know, I encourage you to derive information that you don't necessarily need in the question if they're not asking for it. But if it's unknown information and you can find it using the SUVAT for practice, then go ahead and do it. So we could use from A to C. U was 45 and V was 80, and we've got our acceleration. So we have enough for a SUVAT up here. So we could find we've got 45 here, we've got 80 here, we've got acceleration. So we can find A to C using SUVAT, and you can see the work on that. I'll scroll back down again. And then the other one was find the A to B. Okay, we got A to B. Well, what do we have? We've got time, we've got initial velocity, 45 meters per second, and we've got acceleration, 0.5. So we've got 3 out of the 5, so we could find A to B too. And we would find, okay, so there's A to C, and here's the math for that, and then A to B using the 3 things that I just mentioned. There's the math for that. So it's 2,200 meters from A to B, A to C is 4375. We found that B to C was 2175, and you'll find that if you add 2175 and 220 together, you get 4375. Okay. One thing I do want to mention here is another sort of a mnemonic for when you get units like this. I like to think of it as like a sandwich. There's a piece of bread and there's a piece of bread. And so this is what's in between. And what's in between is on the bottom. In other words, in the denominator. And the bread, or what's on the outside, is on the top. So here's the top data, numerator, and here's in between the pieces of bread is the denominator, or the bottom. So when you get like this kind of unit situation and you're struggling to know how to cancel it out, or you want to make sure you're doing it right, is just remember you've got top and the bottom and the bottom. So anything that can be canceled like that and that cancels, then you've got a top that's got squared, so that knocks out that, and that goes away, and you're just left with meters. So I think this is sometimes, it just depends on how your units are written, but a lot of times you'll either write them that way yourself, or you'll see them that way on a problem when you're trying to follow a problem. So anyway, so let's go to the next problem. It's a choo-choo train, and it starts from rest and accelerates uniformly at 1.5 meters per second squared until it attains a speed of 30 meters per second. And we want to find the time taken for the distance. Oh, wait a minute, my bad. I'm off. I apologize. We'll start here. It's the same problem. A train starts from rest and accelerates uniformly at 1.5 meters per second squared until it attains a speed of 30 meters per second. We want to find two things. We want to find the time taken and the distance traveled. Okay, so for the time taken, first we got to make sure we got a SUVAT or a kinematic problem where we can use SUVAT, and yes, we've got constant acceleration. So we've got one. So we go ahead and write our SUVAT letters. Step 2, we fill in 3 out of the 5. So we've got 1.5 meters per second squared for acceleration. It attains a final speed of 30 meters per second. Okay, and it started from rest, so we have an initial speed of 0 meters per second. And what are we looking for? The time taken. So step 3, we circle that. Step 4, we draw a line through the remaining variable and employ this equation, which is going to be final velocity is equal to initial velocity plus acceleration times time. So we go down here and we just put the information in that we have: final velocity, initial velocity, acceleration, and we're solving for t. And we just algebraically move things around, and as you can see, this is what we get. 20 seconds. Notice again, we've got here's the stuff in between the sandwich, that's on the bottom, and the meters and seconds squared on the outside are on top. So what can we cancel? We can cancel a second and a squared, and then meters cancel. So we're left with s on the top, just like there you go. So that and that cancels and that cancels, again using that. Okay, so let's do the second part of the problem. The train, we already got the information. Now we want to find the distance that this train traveled. Okay, so we know that we actually already know from the previous question the time it took. So we have a good dilemma here. We found this out. We were given this information initially in the problem, so now we're looking for displacement. So this is where you really have to have in your mind these equations well memorized. And the thing to know when you have 4 bits of information is you can use 4 different equations here. There's just one you can't use. So which one can't you use? Well, you can't use the one that's got the s affiliated with it, because that's the missing variable in this equation. So we can't use that equation. So we can use this one, this one, this one, or this one to find the displacement. And of course on a test, or even when you're doing your homework, you want to use the simplest one. And most of the time, you're going to either resort to that one or this first one if you can. Is this situation you can't. But I just wanted to do this to show you that, yes, the SUVAT method is really good when you got 3 out of 5 and you got to find that one equation quickly. But then you really want to have these equations memorized, so when you have 4 out of the 5 variables, when you have it memorized, you know which ones you can use. You've got much more options to use, and you want to use the simplest one. So we're going to use this here to solve for S. So we'll just go down here and use that equation. And we've got final velocity plus initial velocity divided by 2, which is nothing but the average velocity times time. And we've got all that information, so it's just 15 meters per square times 20 seconds. Seconds cancel out, and we find that the choo-choo train displaced 300 meters. All right. And the last problem is a good problem. It's a car. It's being driven along a road at 25 meters per second when the driver suddenly notices that there is a fallen tree blocking the road 65 meters ahead. The driver immediately applies the brakes and giving the car a constant deceleration of 5 meters per second squared. How far in front of the tree does the car come to rest? Okay, so we know that this is a SUVAT problem or kinematic problem because there's constant deceleration. Now notice we've got the word deceleration in this problem, and this car's going down the road. We'll just say it's going to the right. So if that's the case and it's decelerating, it's slowing down, then that means that we've got to be careful about our signs with velocity and acceleration because they're going to be opposite. So if we say that the car's going, hits the brakes, hits the brakes right here, and at that moment in time it was going 25 meters per second, then that means that the acceleration or deceleration, which is nothing but acceleration that's the opposite of the velocity, that's what deceleration is. So we have to watch the sign, even though the problem, and I didn't make a mistake typing this up, even though the problem says 5 meters per second squared, it says constant deceleration. So we have to put a sign there, a negative sign, negative 5 meters per second squared. They've got to be opposite for the car to slow down. So velocity and acceleration vectors. Okay, so we got to transfer that sign in front of the 5. We've got that. And what else do we have? We've got okay, we've got velocity. We have displacement. Okay, we have displacement of the log from the point at which the car hits its brakes. Okay, and so we want to know how far in front of the tree does the car come to rest. So really what we're trying to do is we're trying to find the displacement for this car. Okay, so we're going to have to find another bit of information here. So this is where it's interesting with SUVAT problems, and why I would consider this a little more advanced. What's the other bit of information? We really don't. That's how far the car is from the log, but the car's going to stop before it hits the log, hopefully. So this is not the displacement that we need. We need one more bit of information. So we've got the deceleration. We've got the initial velocity, which is the point that we're interested in the problem. We become interested in the problem, and that's where the car hits the brakes. So that's 25 meters per second when that occurred. And we're looking for displacement, so we're not going to put 65 meters there. We're looking for something less than that. So the car stops with final velocity. So there's our 3 out of 5 now. So we've got initial velocity, final velocity will be when the car stops. We've got our deceleration, which has got a negative sign. Okay, so that's step 2. Step 3, we're looking for the displacement of this car. You know, where is it going to stop before the log? And then step 4 going to be left with time as our variable, so we're going to be employing v squared is equal to u squared. Final velocity squared is equal to initial velocity squared plus 2 times acceleration times displacement. Okay, so let's calculate, and when we calculate that displacement, that will help us answer the problem. So we're going to go down here and we're going to fill in for velocity, final velocity squared. Well, it's going to be stopped after the car hits the brakes. It's going to eventually stop. There's our initial velocity. Here's our acceleration. Again, notice the car said decelerate, but we're not going to call this deceleration. This is just acceleration that's the opposite direction. So it's still A, okay? And we're just going to solve for S. So we're going to subtract minus 25 meters per second squared from both sides. We do that, and then we end up with 2 times negative 5 meters per second squared. We're going to divide both sides by that. So what's going to happen is we end up with minus 625 meters squared. That gets squared and that gets squared. So meters squared per second squared. That's minus divided by minus 10 meters per second squared. Okay, so here's the situation where, again, we've got this, you know, how do we reconcile these units canceling? And we've got that sandwich. There's the bread. So here's our stuff that's in between. That stuff's on the bottom, and then this stuff is that's on top, and that's on top in the numerator. So we're going to cancel out second squared, 1 meter up top, and then that meter goes away. So we're left with meters. So the displacement for the car is 62.5 meters. So the car stopped after hitting the brakes. Hit the brakes here, and the car went, it stopped at 62.5 meters. So it stopped right there. Our log was 65 meters when the car hit the brakes. So we have 65 meters minus 62.5 meters, and that means we're going to have a difference of 2.5 meters. So the distance here, this distance here between the car and the log is 2.5 meters. Okay, good problem. All right, so we've got a few more translational problems to do in the next video series, and I will talk to you then. I don't know if I mentioned at the beginning of the video, I can't remember now, but if you wanted to link to my website or to my or to the first introductory video, part 1, it's in the show more part below the screen, that the viewing screen. Okay, take care, bye bye.